Hello everyone, I am Ali and I am going to discuss my paper on reduced Makespan of scientific workflows with Lambda. We will start by introducing scientific workflows as the main topic of my own talk. A scientific workflow can be defined as a collection of atomic tasks which follow a specific order of processing to achieve a desired goal, where the tasks can be serial tasks to very large parallel tasks. A workflow is modeled as a direct acyclic graph DAG where the nodes are a set of tasks T1, T2, Tn, and the edges represent data dependencies between these tasks as you can see in this workflow. Example on scientific workflows such as montage that is used in astronomy and cybershake that is used in earthquake science, and we highlighted montage as an example because we used it in this study as the test case. When workflow is executed, a schedule must receive dependency constraints, which means each task will wait its predecessors to complete execution in order to start the execution. Each task will do three steps. Firstly, it will read and input data from its predecessor tasks. For example, T3 will read data from T1 in order to start the processing. And then, secondly, it processes the data and finally outputs a result to its successor tasks which are T6 and T7. The scheduling is based on predecessor tasks are triggering their successor tasks when they are completed. There are specific systems for executing scientific workflows, which called workflow management systems. A system that defines, creates, and manages the execution of workflows through the use of software running on different computing resources such as desktops, campus clusters, grids, and clouds. Example on scientific workflow management systems such as Picasso's, that is one of the famous workflow management systems, and WV3. And we highlighted WV3 as an example because we improved its scheduling algorithm in this study as well. These workflow management systems can execute large-scale workflows that contain thousands of jobs. We'll explain Function Platform as a target execution environment. Function as a Service is a commercial cloud platform for running distributed applications for highly scalable capabilities, as well as it provides a platform for customers to develop, run, and manage applications, where the computing resource is automatically provisioned and deprovisioned by the public cloud service provider. In addition, resource management is provided by the platform in a scalable way. Cloud functions have some limits on the amount of resources a function can consume, for example, the amount of computing CPU, the amount of memory RAM, and temporary storage that can use them to run functions. A function is stateless. That means each function invocation is initiated and terminated automatically for each invocation. Examples on cloud functions such as AWS Lambda, Google Cloud Functions, and Microsoft Azure Functions that are the most popular cloud commercial platforms. And we highlighted AWS Lambda as an example because we used it in the study as well. The workflow management system WV3 is capable of executing scientific workflows of three different approaches. Firstly, traditional clusters such as a number of VMs on cloud computing. Secondly, cloud functions that support two types of cloud functions which are AWS Lambda and Google Cloud Functions. And finally, a hybrid mode that combines the traditional clusters with the cloud functions. Here we'll explain the two benefits if workflow are executed on a function as a service systems. Then, the number of concurrent invocations into infrastructure can more closely follow the actual workflow's demands, which means if a workflow has more jobs to be executed, the function as a service can cope with these jobs by executing concurrent Lambda function invocations in order to speed up the total workflow execution time. Secondly, the customer pays for the actual amount of computing resource consumed by executing workflow. WV3 has already shown a large amount of retransfer data behavior, where the scheduling algorithm of WV3 patches jobs to Lambda without scheduling jobs with the precedence requirements to run in the same Lambda function invocation. As you can see in this workflow, for example, the scheduling algorithm of WV3 schedules jobs 2 and 3 to run in Lambda function invocations, and after they completed the execution, the output data files that are generated from jobs 2 and 3 will upload to data storage Amazon S3 as you can see in this figure. WV3 deletes temporary files after each invocation completes the execution. Otherwise, the temporary storage will probably fill up over time. because the temporary storage of Lambda has only 500 megabyte storage. In addition, jobs 4, 5, 6, and 7 will download data dependencies files that are generated from jobs 2 and 3 from Amazon S3 to start the execution. As a result, lots of data dependency jobs transfers can occur during the execution between the storage service Amazon S3 and temporary storage of the function as a service execution environment, and this leads to increased communication costs. I will explain our improved approach. We have changed the scheduling algorithm of WP3 to reduce data dependency transfers. We remove some workflow management system behaviors inside shards and lambdas. The improved algorithm schedules jobs with the precedence requirements to run in the same Lambda function invocation. As you can see in this figure, at the beginning, in step 1, only job 1 is scheduled on a Kinesis shard, where Amazon Kinesis shard is a term introduced by them for queues, where each shard acts as an independent queue for a particular Lambda instance. After job 1 completed the execution, in step 2, jobs 2, 4, and 5 are scheduled on the same Kinesis shard in order to be executed in the same Lambda function invocation, where the jobs will be captured in order by the shard and Lambda. Afterward, Lambda will immediately getting these jobs in a single batch, and then they will be executed sequentially inside Lambda invocation, where job 2 should be executed before jobs 4 and 5 because a schedule must receive the dependence constraints of workflow. As a result, the improved algorithm avoided transfer the output files that are generated from job 2, where jobs 4 and 5 will be utilized these files in the same function invocation. And the same for job 3 and 7 are scheduled on the same shard to run in the same Lambda function invocation. Job 6 is not scheduled because it has two predecessor jobs which are 2 and 3. And finally, in step 3, only job 6 is scheduled on shard 2 in order to run in Lambda 2. And in this step, the algorithm selected the shard 2 because it has received smaller amount of jobs than shard 1. The algorithm counts the jobs that are sent to each shard in order to balance the workload across Kinesis shards, leading to balanced usage of all Lambda instances. There are lots of configurations for the small-scale montage workflow. The biggest change in memory, and that is shown in this bar chart. The experimental results of the improved approach are outperform the WV3 for all memory sizes except the memory size half a gigabyte, because testing with smaller montage workflows does not show significant differences with regards to the total execution time, where our approach needs lots of retransfers data behavior to show the reduction in the execution time. Here I will explain a particular setup, which is the 6-degree montage workflow. We have selected this workflow for two reasons. Firstly, WV3 has already shown a large amount of retransfer data behavior by executing this workflow. Secondly, we need to demonstrate WV3 does have this issue. So we have chosen this workflow, which is large scale and has over 8,000 jobs with a total size 38 gigabytes, including a data dependency size. We measure the total execution time of the 6-degree montage workflow on Amazon Lambda. The configuration details for the large scale montage workflow, as you can see in this table. The memory size was 3 GB and the shard number was 30. These settings were selected due to the large number of jobs of the 6-degree montage workflow. The experimental results show that our improved system can outperform WV3 in most cases. At best, in contrast to the original, we have achieved about 10% shorter of the overall workflow execution time. As you can see in this bar chart, the total workflow execution time of the improved algorithm is 1001, while the total workflow execution time of WV3 is 1109. For experimental results that are shown in this bar chart, we performed the same experiment 3 times and report the average number as the test result. In conclusion, firstly, we have modified the job scheduling algorithm of WV3 on AWS Lambda to reduce data dependency transfers. Our modified algorithm schedules jobs with the precedence constraints to be executed in the same Lambda function invocation. Therefore, successor jobs can utilize output files that are generated from their predecessor jobs in the same Lambda function invocation. This will reduce the overall workflow execution time. Secondly, we have evaluated the improved scheduling algorithm and the original algorithm with large-scale montage workflow, which is 6-degree workflow. Finally, the experimental results show that our improved scheduling algorithm can reduce the overall execution time of scientific workflows on the Lambda platform, in contrast to the original algorithm of the W3. Thank you for listening. Any questions?